behind this dazzling glare is all this activity, eruptions, explosions, interesting physics. It's the star on our doorstep. The sun itself is about 110 Earths lined up side by side, and it has a stronger magnetic field, so that balloons out into space and fills this enormous area. We are sitting in its atmosphere, and its atmosphere is variable and gusty and dynamic.
We're in two atmospheres. We're on our own atmosphere and we're in the sun's atmosphere.
You're listening to the Met Office Deeper Dive. In-depth conversations with the world's leading weather and climate experts.
Hello and welcome to the Met Office Deeper Dive. This time I'm joined by Professor Lucie Green, solar physicist at UCL's Mullard Space Science Lab. Welcome to the Deeper Dive, Lucie.
Thank you.
Loads of stuff to get stuck into today. Not only are you a solar physicist, but of course you're a science communicator. You might recognise Lucie from various TV programmes, including The Sky at Night. Written a book as well, 15 Million Degrees, Journey to the Centre of the Sun. And what comes across in your science communication is your enthusiasm for your work, the sun. And I'd love to know, have you always wanted to be a solar physicist? When did this passion begin?
Yeah, well, I guess like many people, I kind of followed my nose from leaving school, and I took a sort of traditional path, went to university, did physics and astrophysics. And it was there that I realised how interesting the sun is as an astrophysical object. And I was kind of surprised that people never really talked about the science of the sun until I got to university. And even then, it wasn't really a focus of the studies. But I had the chance to look through a dedicated solar telescope and see the sun using a particular filter. And that's when I saw the sun's atmosphere and how interesting it is. And I thought, wow, there's lots of questions I've got. And that kind of set me on the path of being interested in the sun, and then realising that you could have a career as a solar physicist. And I haven't looked back since. And that was well over 25 years ago.
Yeah, and you said that, not many people were thinking much about the sun. It's omnipresent in the sky above us. We see it all the time, in some countries more than others. But we don't realise, we don't think on a daily basis about how active it is, do we?
Exactly that, and I think that was the kind of transformation for me, was that somehow we are so familiar with the sun. We know it's there every day. In Britain, we're obsessed. Are we going to see the sun? Is it going to be sunny today? But because it is so dazzlingly bright, we can't look at it directly. So you have to have a specialist telescope. So for me, it was this object that we were both really familiar with, but at the same time didn't understand at all. So then when you do realise that behind this dazzling glare is all this activity, eruptions, explosions, interesting physics, when you realise that, for me it was a kind of natural, well, it's the star on our doorstep. It's the only star that we can spatially resolve and study in detail and get up close to. So this should be the star that we really focus on, I would say, and characterise, and indeed we do. And then everything we learn about our sun, okay, applies to our sun, but it applies to stars more generally as well. So some people kind of call it a bit of a Rosetta Stone for them working out what other stars are doing.
And do we know how it compares with other stars? Is it a particularly active star or less active? How would you say it compares? When you look at the grand scheme of things, it's not a particularly big star. There are definitely stars much more massive, much larger in size, and stars much smaller. There are stars that live longer, stars that don't live as long, stars that are more active, stars that are less active. So it doesn't really, I don't think it stands out in terms of its kind of character or characteristics. But still, it shows all these active properties that tell us about other stars. So, and maybe this is why life has evolved around our sun. Maybe it is because it's not particularly active, or it's not too inactive. Maybe it is a bit of a sort of Goldilocks star, that it is just right. But that's what it is.
We don't obviously want it to be too active, right? At a previous deeper dive, we spoke to Craig Rogers, who explained at great length how activity on the sun affects the Earth and some of the risks that are involved with activity from the sun. We're going to focus in this conversation more on where that activity originates and what causes the activity on the sun. We don't want it to be too active. What if it wasn't active at all? Would there be an issue there as well?
That's a good question. I mean, if it wasn't active at all, well, that probably implies a star which is maybe coming to the end of its life, because the activity comes from the fact that the sun has a magnetic field, and stars have magnetic fields. So I'm not sure whether an inactive star would have been a problem for us, but you're right, certainly an active star, too active, is a problem, could be a problem.
So the activity is a consequence of the fact that it's got a magnetic field, and all other stars, they have a similar setup, do they, with the magnetic field that is causing bouts of activity?
They do. So magnetism seems to be a kind of fundamental building block of the universe. And it arises when you've got charged particles and motion of those charged particles, and you generate magnetic fields. So as far as I know, it's still an open question about how the kind of cosmic magnetic fields really originated if you go all the way back to the early universe. But certainly once you've got stars and you've got hot material, ionized material, that has formed from the collapse of these enormous gas clouds, which I think are thought to have had magnetic fields pervading or permeating through them. So you collapse these gas clouds, that brings the magnetic fields in with it. So when stars form, they should have some magnetic field within them. But then because stars are themselves made of charged particles, ionized materials, electrons, protons, the flow of these charged particles are electric currents. And so they can maintain and amplify magnetic fields. So our sun, for example, is thought to have probably some primordial magnetic field running through its core that was that swept up in its initial formation, plus this overlying sort of modulation and evolution of the magnetic field that goes on year after year. So when you're studying stars, and indeed other cosmic objects, you need to take on the challenge of understanding magnetism and then applying that physics to these cosmic environments.
And the magnetic field, is that primarily found on the surface of the sun, or is it in the atmosphere? Where are we looking for this activity?
So I think it's probably mindful to think about the Earth as a sort of starting point for conceptualizing that. So we're familiar with the Earth having a magnetic field, and we think about it, being generated inside the Earth via molten metal flows, but that the field then emanates out through the Earth, comes through the surface and into the atmosphere and into space. So the magnetic fields are everywhere. They might be more concentrated in some regions and maybe less so in others, so maybe more concentrated around the poles. And for the sun, it's the same, that there are magnetic fields that run through the sun, and they come out through the surface and then they extend into space. It's just that the magnetic field of the sun is enormous. The sun itself is about 110 Earths lined up side by side, and it has a stronger magnetic field, so that balloons out into space and fills this enormous area. So I sort of think about the magnetic field as permeating the sun and permeating the atmosphere of the sun and expanding out like a bubble into space.
Yes, so it extends far beyond the sun's surface, well out. Does it kind of fully encompass the inner planets as well? It
does, and I think this is one of the kind of aspects of the sun that I find quite profound, because the magnetic field extends out into space. It goes beyond the orbits of all the planets, so reaches out to Earth, Mars, Jupiter, Saturn, Uranus, goes all the way out. And I'm not sure if it would be a bubble in shape, or if it's a bit like a kind of teardrop because the solar system has some motion, so maybe it's sort of, you know, a bubble-like on one side and has a tail drawn out on the other. We don't have the data.
Because the solar system is moving in one direction.
Yes.
So it's possible that the magnetic field will have a tail that in the other direction.
So like a kind of windsock, maybe sort of drawn out. But it probably extends at least 40 billion kilometres from the sun. So it is way beyond the orbits of the planet. So that means that, the consequence of the sun's magnetic field and its atmosphere extending so far into space is that the Earth is sitting in the atmosphere of the sun. So we are, we're on the Earth, we've got the atmosphere of the Earth around us, but then like sort of, babushka dolls, you've then got the atmosphere of the sun around that. And that's what I find really lovely, because again, sort of going back to this thinking that the sun is over there and it's dazzlingly bright and we don't really know it, we sort of think, oh, we're disconnected from it except for the light we get. But that's not really true. We are sitting in its atmosphere, and its atmosphere is variable and gusty and dynamic, just like the Earth's atmosphere is. So that leads to this concept of space weather. We've got Earth's weather, the Earth's atmosphere, space weather in the sun's atmosphere, and we're affected by that.
We're in two atmospheres. We're on our own atmosphere and we're in the sun's atmosphere.
Yeah.
It makes me feel like we're even more vulnerable than I thought. This small rocky planet that is in the sun's atmosphere.
Yeah, and this kind of perception was transformed in the space era, because prior to that, well, firstly, we didn't have the theories to tell us that we sit in the sun's atmosphere. And secondly, we didn't have the data, because we didn't yet have any spacecraft leave the Earth's atmosphere and magnetic field and go beyond. So when I, was reading papers from pre-1960s, you have a totally different description of the sun and the Earth and how they might be connected as we do today. So there's something really lovely about the fact that the knowledge has progressed so profoundly and transformatively over the last 60 years or so.
And how did we come to the discovery, or the idea that the magnetic field extends 40 billion kilometres away? Because I'm guessing that's not something you can measure out to 40 billion kilometres.
No, that's right, and it's not intuitive. So again, we could start with the Earth as an analogy. Now, the Earth's atmosphere is sort of held onto the Earth. As you go up in height, any hot molecules or, with high motions would be able to escape the Earth's gravitational field and go off into space, and what's left sort of stays confined to the Earth. With the sun has an atmosphere of ionised gases and a magnetic field, but the thermal conductivity in that atmosphere is very high. So that means that the temperature stays high to high heights, high altitudes. So the atmosphere of the sun is about 1 million Kelvin, 1 million degrees Celsius. And the high thermal conductivity keeps that temperature high out to large distances. But that means that there is this sort of high thermal pressure to the atmosphere of the sun, and it can push out against gravity, the sun's gravity. So low down in the atmosphere of the sun, the hot gas is able to be held by the sun under its gravitational pull. But as you go higher and higher, the gravitational pull drops off, but the thermal pressure doesn't drop off so rapidly because the thermal conduction is good. So when you get to a certain height, the atmosphere of the sun is literally flowing out into space. It cannot be held onto by the sun anymore. And that's what generates this enormous sort of sphere of influence of the sun, the heliosphere.
Because the sun's atmosphere is hotter than the surface of the sun, isn't it? And this is something that, well, first of all, what is the sun's atmosphere? What's the surface? Because it's essentially a ball of gas, isn't it?
Yeah.
Unlike the Earth, where we've got a solid surface and a gaseous atmosphere. So what's the difference between the two?
Yes, this is what I teach my students on the solar physics module. So you're absolutely right. I mean, the sun is just this tenuous ball of gas. And at some point we give it the name that it has a surface and then an atmosphere, and then it goes into this outflow into the solar wind and carves out this enormous space in the universe. But the way we would assign layers really comes down to the properties of the gas, of the plasma, and also how light is able to move through these layers. So inside the sun, we have the process of nuclear fusion, which a lot of people I think have heard about, maybe familiar with, where you're colliding particles together and that releases photons of light. And they kind of like ping around the sun and eventually they work their way out. But they have quite a hard time because the gases inside the sun are dense and they're electrically charged. And so the photons of light interact with them. But when you move to a certain distance from the core, the density of the gas drops, the temperature drops, its properties change. So you get to a certain point where actually these photons of light don't struggle to move through the gas anymore. They can move freely. So we would say the opacity has changed. So what was an opaque interior suddenly becomes transparent to these photons. And that defines the surface. Really, it's a visible surface. It's not a solid surface. It's a very low density gas. But the photons are suddenly able to stream out into space. So we can look at the sun and the photons from the visible surface can get to us. 150 million kilometres through space. So that's how we would set the surface. It's a visible surface. But of course the gas is, is still there in the atmosphere. It's just getting less dense and hotter. So the visible surface has a temperature of about 6,000 Kelvin, and then you go up in temperature in the atmosphere to a couple of million Kelvin. So what we tend to do is assign layers according to their properties. So we've got the photosphere, the visible surface, then we've got the layer just above that we call the chromosphere, and that's something that people who are into total solar eclipses may have seen. It's like a ring.
Diamond ring, yeah.
Yeah, that's right. And then when the moon totally blocks the sun, you get this kind of reddy glow, and that's the light coming from hydrogen in the chromosphere, so a low down layer of the sun's atmosphere. And then after that, suddenly the temperature shoots up. So that gives us another kind of way of defining a new layer. And then we come into the corona where the temperature's really hot, and that's the kind of hot outer layer that then you would see during a total solar eclipse, as that kind of pearly white glow around the sun.
Yeah, because I read in your book that the amount of time it takes a photon to go from the centre of the sun to the surface versus from the surface to the Earth.
Yeah.
And I guess that what you talk about there, the density of the interior of the sun from the surface to the centre, that makes that journey so slow compared with the rest of it.
Yeah, I would sort of imagine it as being a bit like a pinball game. So you sort of ping off your ball bearing and it sort of clatters around, being bounced off of flippers and whatever in the pinball machine. And that's a bit like the photon. But the photon is colliding with electrons inside the sun, and those electrons are scattering them, making the photons go in all directions. But then when you get to the photosphere, actually the electrons that were freely moving around inside the sun start to be bound up in ions, and they're not freely available anymore. And so at that point, the photons are like, oh, I don't have any electrons to scatter off anymore, and off they can go.
I mean, it's mind-boggling, isn't it? The different layers of the sun and the temperature differences I always find extraordinary. You mentioned 6,000 Kelvin for the surface of the sun, which actually sounds quite cool compared with the rest of it. What I don't understand is why it gets so hot when you get into the atmosphere. Because presumably you've got an incredibly hot interior, then it gets cooler as you go further out towards the surface. Why does it then get hot again?
So that comes back to magnetic fields. If the sun didn't have a magnetic field, it wouldn't have this hot atmosphere. So what we understand so far is that these magnetic fields, and we talked about them sort of being in the sun and permeating through the sun and into the atmosphere. So in the surface of the sun and below the surface, the gases, the plasma is moving. So there are convective cells bringing up hot plasma that then radiates photons, cools down and sinks back into the sun. So there are all these kind of mechanical motions in which the magnetic field is embedded. So there's all this mechanical energy and it's moving around the magnetic fields. And those magnetic fields somehow are able to transport that magnetic energy into the atmosphere and change its form from being in mechanical energy to being in thermal energy of the hot gas.
Right.
And they're the details that are being worked out at the moment. What are those physical processes? It might be something like waves. So when I conceptualize magnetic fields, you can conceptualize a magnetic field line, and a bit like a kind of guitar string, you could pluck it and a wave would move along it. So it might be that waves moving along magnetic fields can transport this energy from sort of in the top layers of the sun up the magnetic fields into the atmosphere, where then it's deposited somehow. So that's one way. Another way is that all these sort of fluid flows, they can sort of tangle up the magnetic field. So again, if you think of sort of field lines, if you have that concept, and you might move around the foot points of your field lines, you might start to braid them together. And when you do that, you can cause or create conditions for this process that gets called magnetic reconnection. So it's a bit of jargon in the plasma community. But this process of magnetic reconnection sort of breaks and joins these field lines. But at the same time, it releases energy that was stored in the magnetic fields and transforms it into plasma heating. So there are these sort of two camps, waves being guided by magnetic fields or breaking and rejoining an energy release, magnetic reconnection, but all having their kind of origin in the plasma flows in the outer layer of the sun. So I think we've made some really good progress in understanding why the atmosphere of the sun is so hot, but it's the details now. How much energy? How do these mechanisms work? Do they both operate, both camps? Does one dominate in some places and one in another? And there's a lot of great work in the UK that's looking into these processes.
So plasma, that's essentially where you've got atoms that have been heated so much that they lose their electrons, isn't it? And that fundamentally then causes the magnetism.
That's right. So yeah, the word plasma refers to a gas which has been heated so that you can start to tear atoms apart or ions apart. So you eject your electrons. So you've got negatively charged electrons and positively charged nuclei. And when you have flows of charged particles, you have electric currents and then you have magnetic fields.
Yeah. And one area of research that you've been involved in, something called magnetic flux ropes. Is that related to the guitar string analogy that you were talking about there?
It's more related to the reconnection,
right.
So the breaking and joining of magnetic field lines. And so what the sun seems to do is have two sort of fundamental structures in its magnetic field. One is an arch that might come up from the surface of the sun into the atmosphere and back down again. But if I had a bundle of field lines, I could sort of rotate one of the foot points, and field lines that were aligned with each other might sort of start to twist around themselves. And that's what we mean by a magnetic flux rope. It's something where the magnetic field is helical. And the sun, well, we had a question for many years, could the sun create these magnetic field configurations? And I think what we've been seeing in the last sort of decade or so is that yes, the sun can make these twisted field configurations. And when it does so, it's a great way of storing energy in the atmosphere of the sun. And then that energy can get released to power activity events that we see.
And do they twist it because the sun is rotating at differential rates depending on latitude and so on?
Yeah, I mean, it could be. Inside the sun, where there are strong magnetic fields, you can get twisting that way, and that's thought to happen. What seems to take place, though, is that these twisted magnetic fields that form inside the sun, they can sort of pop up so they can start to ascend through the sun, get to the surface, and then burst through. But they only partially burst through, so you actually have to rebuild your flux rope in the atmosphere of the sun. So there's this kind of, you build a flux rope inside, part of it pops up and emerges, and then you sort of rebuild it again in the atmosphere of the sun. But the sun seems to do this.
So there's this theory then, and a lot of relatively recent research, partly done by you, about these magnetic flux ropes being the cause of a lot of the solar activity, including coronal mass ejections.
Yes, so this is where I think we've had some really interesting work, because coronal mass ejections are a bit counterintuitive, because you've got to get the mass of a mountain, so the same mass as is in a mountain, ejected from the sun, which has a huge gravitational pull. So you need to send it away from the sun at speeds of millions of miles an hour, a couple of thousand kilometres a second. So it's a real, it's a challenge. Where does that energy come from? And what are the forces that will lift all this plasma, all this gas at those speeds away from the sun? And it wasn't clear how the sun did this, but some people started to develop theories that maybe these flux ropes were important or relevant for this ejection of mass. And that's because if you have a flux rope and you analyse the forces on that structure, which are actually magnetic forces, they can have an upward force. So that naturally makes you think, well, okay, if that upward force can dominate, maybe they could be the way to eject stuff from the sun. And so sort of, a series of studies, I mean, it is an international effort, but the conclusion is that people can create simulations of flux ropes in the atmosphere of the sun, and they can make them erupt in the way that we see eruptions from the sun happening. So on the same time scale, same speeds and so on. So theoretically, it looked compelling. But then what we need to do is show the real sun does this. So it's one thing to say it's a theory and we can recreate it in a computer, but does the sun actually operate this way? And it's really hard to measure magnetic fields on cosmic objects. And it's really hard to measure magnetic fields in the atmosphere of the sun. So we have to use a kind of series of indirect methods to identify these flux ropes. But we have developed them, and I think the observations do support, in many cases, these twisted magnetic field structures, these flux ropes, forming on the sun and then literally erupting into space and scooping up the gas, the plasma from the atmosphere of the sun and taking it out into the solar system. So
the theory that this was going on happened before we could observe it, before we could find any evidence of it happening?
Yes, well, I suppose the things sort of developed hand in hand, but we were certainly getting theories being well developed, sort of the early 2000s. And at that point in time, we had a really important mission launch called SOHO, so Solar Heliospheric Observatory. It's a joint European Space Agency and NASA mission. And that started gathering really good observations. And I remember being at a conference and people showing lots of observations of these eruptions from the sun. And somebody saying, look, we've got all of these observations. Where's the theory to explain what's happening? And then we had a kind of, I don't know, people say, yes, okay, right, let's work on the theory. So then they developed the theory. And then that gave us a set of kind of quantities that we could then look for in the data to test the theories. So I think these things sort of go hand in hand. You do have observations, but you need a theory, but you have to discriminate between the options. And so the theories need to provide you with observations that you can look for to directly test which one is right.
And we're getting more and more observations now, aren't we? We're sending up more and more instruments. Can you tell me a bit more about Solar Orbiter and Hinode and those instruments? Yeah,
so we are lucky because I think the importance of the sun for science and for space weather in our lives means that nations are, will invest a lot of money in sending spacecraft up to look at the sun. So Solar Orbiter is Europe's latest mission to the Sun, and Solar Orbiter is in orbit around the Sun itself and gets as close to the Sun as the planet Mercury does. So this is our chance to kind of get up close and personal with the Sun, look at it from close up, and measure those outflows of gas that we talked about coming from the atmosphere of the Sun. Hinode is a Japanese spacecraft that was launched a whopping 20 years ago now, launched in 2006. And that is a mission that, even though it's a Japanese spacecraft, it's got American contributions, British contributions. So the department I work in led one of the telescopes on board. We also have a big contribution to Solar Orbiter. So in the UK, we are designing, building and providing telescopes for these international missions. And that's fantastic because it means, you know, being a scientist in this country, you can have your research questions, but then you can, you know, help define what missions are the next ones to answer those research questions. So we're always working with the European Space Agency, working with colleagues in NASA and so on, and colleagues in Japan to help devise and make real the next missions.
Just bring it back to impacts on Earth. You mentioned that, you know, we're all really interested in the Sun and its activity because it can be so risky for the Earth. We covered that with Craig Rogers earlier in the year. Will these additional observations and new technologies help with making predictions about when these coronal mass ejections are likely to happen?
They will. So we will approach this from two different directions. One will be from a research perspective, in that we will be analysing data to help understand the physics of really why these eruptions occur. So we talked about flux ropes and the kind of building blocks of magnetism and getting the right forces to propel the plasma upwards. But the details of how do you build the flux rope, at what point does it become unstable and erupt, all of that is still to be understood. And the Sun is messy and complex, and there's all these details still to work out. So we are still pursuing that avenue. But at the same time, we want to have forecasts that will be carried out here at the Met Office. Mm-hmm. And so a forecaster can say, I look at the data, I use this model, and I predict, or the model says that there's a 20% chance of a coronal mass ejection taking place tomorrow. And in order to support that initiative, there's another mission that will be launched called Vigil. And that is a European Space Agency mission, which is dedicated for space weather forecasting. It won't launch until the early 2030s. So we've still got a few years to go. And it's a mission that's been worked on for several years already. So these are quite long timescales that need to play out between concept and launch. But the Vigil mission will give us a different perspective on the Sun, literally, because, you know, we've got our perspective from the Earth, but Vigil will look from a 60-degree angle away from the Sun-Earth line. So we'll be able to see more of the Sun. We'll be able to see coronal mass ejections leaving the Sun and heading towards the Earth. We'll look at that from the side with Vigil. So Vigil will allow us to have sort of dedicated observations, and we will prepare models for Vigil so that space weather forecasting from an operational perspective will be possible. And I really hope that includes forecasting CMEs.
What kind of timescales are we talking about in terms of, you know, improving our forecasts? Is it an extra 1-2 days, perhaps longer?
Good question. So, I mean, at the moment, we don't forecast the occurrence of a coronal mass ejection at all. I would hope that by the time we get to Vigil, we will be doing that. In addition, because Vigil shows us more of the surface and atmosphere of the Sun than we can see from Earth, we will sort of get maybe 4 or so days more advanced warning of at least potentially active regions that will be rotating round then to be seen from the Earth view. So I think we will hopefully get a CME, the forecasting of a coronal mass ejection, and if we could get that a day before it happens, that would be amazing. I think that's probably a challenge, but with Vigil, I think we'll start to have the right data to track regions on the sun for longer and understand their eruptive potential.
Mm-hmm. Thinking about predicting changes in the sun further ahead, there's this cycle, isn't there, the 11-year cycle. Can you explain why is there a cycle, and is it exactly 11 years, or does it kind of chop and change? Does it drift through time?
The 11-year cycle refers to the sort of ebb and flow of the magnetic field of the sun on a global scale, and these fluid flows inside the sun that we talked about take the sun's magnetic field, and they can, it's a bit like sort of pulling on a string, they can wind up the magnetic fields, and they wind them up and they amplify them, and then regions of strong fields start to emerge through the surface into the atmosphere. But then once they're there, those fields start to disperse and get sort of redistributed over the surface of the sun, again by fluid flows. So all the time, the fluid flows of the sun are evolving its magnetic field, and it does so on a roughly 11-year timescale. As average though, could be 8 years long, could be 15 years long. So it's a magnetic cycle. Uh-huh. And at the start of the cycle, the sun's magnetic field is relatively simple and weaker. And as the cycle progresses, the sun's magnetic field strengthens and becomes much more complex. But then it starts to die down again and becomes simpler. And then so every 11 years, it's kind of pulsing. And it's all to do with the fluid flows of the sun. And again, the details are still being worked out, and missions like Solar Orbiter are designed to try and answer open questions that we have about this 11-year cycle. So for example, when magnetic fields emerge from the interior to the surface and then get redistributed, little fragments of magnetic fields get carried to the poles of the sun. And if you imagine we're sat here on the Earth looking at the sun's equator, we can't really see what's happening at the polar regions. So Solar Orbiter, as well as getting close to the sun, is put into an orbit where it will be tilted and be able to see, have a better view of the poles than we have here on the Earth. So in the coming years, Solar Orbiter will allow us to track how these little magnetic fragments are moving towards the poles and basically setting the scene for the next 11-year cycle. At the moment, we don't have those observations.
Will that make it possible, and I don't know what what our ability is at the moment, but would it make it possible to predict the strength of the next solar maximum, or is that beyond the realm of possibility?
No, I think that that's the data that's needed. I mean, I don't work on solar dynamo, but what seems to be the case is that these magnetic fields at the poles are the seed from which the next cycle grows. So if you can see how these little weak magnetic fields are being transported to the poles, what the strength then is, how they build up, I think then you'll know what's likely to come next. So at the moment there are really good models that will aim to predict the size, duration of the next solar cycle. But it's really hard because we lack these observations at the poles. And so far we have different approaches, different models, and it's a great kind of source of focus in the community to see people's predictions and then see over time whose one is right. And I mean, although they are brilliant, the cycle that we're in now is bigger than expected, according to some models, and the cycle before was smaller than expected. So we've still got some work to do, but the models are developing, and then we'll have better observations to feed into those models.
Any idea about the next solar maximum, when and how big it will be?
That's a good question. Again, I'm not sure. I haven't followed beyond the one that we're in, which is cycle 25, and we've just sort of, we're at solar maximum now. I'm not sure what's coming next. Google will tell you though.
Yeah. Now, a lot of people watching this, because this is a weather channel, will be aware that we've had grand solar minima in the past. I find this fascinating, the fact that we had decades where barely a sunspot was observed. What causes these periods in which the sun becomes less active versus, you know, more modern times when it's been much more active?
They're really interesting times. So when you look back over the sunspot record, you can use the number of sunspots, so these dark patches on the surface of the sun, which we know today are actually regions of strong magnetic field. So they are like a visible manifestation of where we are in the solar cycle. You have very few spots, you're at cycle minimum, lots of spots, you're at cycle maximum, and then it drops off again. And we've got records of sunspots going back, well, let's say decent records maybe a couple of hundred years, but really you could stretch it back to the early 1600s when the telescope was first used to look at the sun and these sunspots were observed. So you see this ebb and flow, this 11-year cycle with the sunspot number going up and down. And then when you look back over these centuries, you see times where the sunspots disappear. So the most famous time is the Maunder minimum at the end of the 1600s, early 1700s. And it's telling us that something inside the sun is changing so that you don't get these strong magnetic fields being generated, because it's the strong fields that then rise up and burst through the surface and form the sunspots. So the cycle seems to switch off. But equally, the sun is not completely dead, because the cycle then starts again. So the sun does seem to have this ability to make a sort of, the cycle, but also small cycles and times where the cycle seems to switch off and then it comes back to life again. And I think that's one of the big questions in solar physics, is what's happening inside the sun to mean that its dynamo kind of goes into this quiet phase for some decades, but then is able to pick up again.
It seems like the more we find out about the sun, the more there is to find out. What are you most excited about learning about the sun in the next few years, few decades?
Definitely the details of the solar cycle and the solar dynamo. I think that's the big open question, and it's such a fundamental one because stars have solar dynamos and stellar cycles. We see that. So if we can unpick the processes on the sun, we can apply that to other stars. So that for me is a big one. And then closer to home, it's forecasting coronal mass ejections. That's the one I want to crack in the coming years.
And that will have such a big impact on we people on Earth, right?
Yeah, exactly. Because if we can do that, then we can change and improve our space weather forecasting.
Really, really fascinating to talk to you about solar physics today. Thank you very much, Professor Lucie Green. Hope you enjoyed it this week, and let us know what you think in the comments. Send us any questions you have about space weather, about solar physics, and we'll try our best to answer them and get back to you. But thank you for watching. Bye-bye.